Hello everyone and welcome to another video by Mahmoud Noor. This is Noor Yudarris. Today we'll be speaking about chemistry's own atomic structure and periodic table. Some little itty bitty simple stuff. So shall we get started? So nucleons um, are the atomic mass that consists of both protons and neutrons. They each weigh 1.66 times 10 to the power of negative 27 each. Next we have isotopes. Isotopes are two atom variation with different number of neutrons. Okay, so isotope, for instance, carbon 12 versus carbon um, 13, for instance, something like that. Here on the periodic table, let's say you get an element. How do you basically dissect the element? So the atomic number is equivalent to the number of protons the atom has. This is the atomic symbol, and the weight. This is the atomic mass. All right, not the atomic weight. Sorry, the atomic mass. All right, this is the average mass. Next, we have an anion. An anion is a negatively charged and cation is a positively charged. Next we have protons and neutrons. The protons and neutrons, they're held down by strong nuclear forces or SNFs. So basically positive charges, they push against each other. So protons are together and they push against each other. Uh, they want to repel, they want to get as far away from each other as possible, but they're held down by strong nuclear forces. There are also unstable nuclei, and an unstable nuclei is radioactive. So how does it become stable? It undergoes a radioactive decay to become stable. There are five types of radioactive decay that we'll be speaking about today. There's alpha, there is beta, beta plus, and beta negative. There is gamma and electron capture. So let's start with alpha decay. Alpha decay is atomic number of the parent is decreased by 2 and the atomic mass is decreased by 4. So that's the alpha particle. It's basically 4 for the atomic mass on top and 2 for the number of protons. So let's say you have carbon 12, or like, sorry, no. Let's say you have a, here, this is a 210. So a 210 is a element, and not sure which element it is right now, but let's say we have 210. Or here, a better example. Let's say you have nitrogen. Okay, so you have nitrogen. Okay, and then nitrogen undergoes a alpha decay. But what is nitrogen actually? Nitrogen is 7. So it has 7 protons because of its atomic number, and its atomic mass is 14. So 14 and 7. Okay, and then it goes alpha decay. It becomes a carbon. Okay, or actually, is that the right answer? No, it's not, because we said it loses 2 and it loses 4. So it loses 4, so it becomes 10, and it loses 2, so it becomes 5. So what atom is that? That is boron. So it undergoes alpha decay to become boron. Okay, so it loses 4 atomic masses and 2 protons. That was a trick question, everyone, to see if you're focused on the video or not. Okay, next we have a beta decay, negative beta decay, which is unstable nucleus that contains too many neutrons, okay? And it doesn't contain as many protons. So you want to convert the neutrons into protons and electrons. Basically, essentially, the beta decay has the same atomic mass, but the atomic number changes. So in the negative beta decay, the atomic number is 1 greater than the parent. This is because we're adding more protons. So here we have um, carbon 14. Okay, no, carbon is not 14. Carbon is 12. Sorry, my bad. Carbon is 12. But this could be, for instance, an isotope of carbon, okay? But you add 1 and it gets converted to nitrogen and an electron is lost. So basically, electron is lost because you converted a neutron to both an electron and a proton, okay? And the atomic number increases. Next, you have a beta plus decay. in which the nucleus contains few neutrons, but more electrons and protons. So you convert the protons and the electrons to um, neutrons. Okay, it's also same atomic mass, but it's now one less, and instead of electron, it has a positron or positron. It's an electron antiparticle, which is gained. And you guys have it here. Alpha decay is essentially the only one with the atomic mass change. Next, you have electron capture, in which you want to increase the number of neutrons. So how do you do that? The electron is captured from the nearest shell, so that's the N1 shell, and it converts proton into neutron, and the atomic number decreases by 1. So basically electron capture is kind of similar to a beta positive decay, but here it has an electron. It uses an electron instead of a positron. So here it uses an electron and converts a proton to a neutron. No positron gain, no electron gain. Actually, the electron is used. And then lastly, we have the gamma decay. Gamma decay occurs after alpha or beta decay, where excited state undergoes decay and gives off gamma photons. So here you have Si undergoes beta negative decay. We said beta negative decay, it increases, you add one more proton. So negative, you add, positive, you decrease or remove. So it gets converted to P, and then now it's in an excited state because of the star. Okay, so in order to remove it from the excited state, undergoes gamma decay and then emits gamma photons, but stays the same. No change in the atomic mass, no change in the protons. Next you have half-life. Half-life unit is T times half, which is the time it takes for 1/2 of the sample to decay. The shorter the half-life, the higher the decay. There's also exponential decay curve, which is this one. So let's say I give you a sample of 100 grams of, I would say 100 grams of, for instance, carbon, and I tell you that every 24 hours this carbon gets decayed. Alright, so tell me after, for instance, 48 hours, how many carbon will there be left? So you start with 100, and then you know that every 24 hours it gets halved. So what's half of 100 in the first 24 hours? That's 50. Okay, and the question is asking, oh, so 48 hours, so that's 24 and 24. 24 and 24 hours, so the 50, again, it undergoes another one. So after 48 hours, there will be 25 grams of carbon left. So that's essentially what half-life is. Next you have emission photon. Emission photon is h times frequency, and h is a constant, a Planck's constant, 6.63 times 10 to the power of negative 34, or it could be also h is equal to the speed of light divided the wavelength. So when photons are absorbed, electrons jump from a higher level ground to an excited positive stage. So here it gets absorbed. It jumps, for instance, from N1s, for instance, to N2s. That's when they absorb the photon. But what if the photons are emitted from the carbon? Okay, they're emitted because electrons kind of emit them. They get relaxed and they drop to a lower energy state. It's basically from higher to lower, and energy gets released. It's negative. Alright, so Bohr's equation is used to calculate the energy between the shells, and it's negative 2.178 times 10 to the power of negative 8 divided n, which is the shells to the power of 2. So let's say you're going from the third shell to the first shell energy level. So you got this negative, it's, by the way, it's final minus initial. The final is 1 because you're going to it. So basically it's negative 0.178 times 10 to the power of negative 18 divided 1 squared minus negative 2.178 times 10 to the power of negative 18 divided 3 squared, and the answer is going to be in the negative because photons are emitted. You're going from a higher to a ground level. Negative 1.936 times 10 to the power of negative 18 joules. Next, you have the electron configuration rules, where we place the electrons in the subshells. Alright, first off, the off-boot rule, which is the electron occupy the lowest orbital shell, then fills in increasing order. So, as you can see here, this is the way it goes, kind of like I would say like spiral, you would say, kinda, yeah, or kind of zigzaggy. Alright, so you start at 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then actually you go to 3d, and then 4p, and then 5s. So this is the way it goes, just kind of zigzaggy. And then you got hands, which is electrons in the same subshell must occupy before pairing up, which means that you have, let's say you have the p subshell, you need to occupy each single one of them before you pair them up, like that. And then next we have poly, which states that there's no more than 2 electrons in a given orbital. Next you have anomalous electron configuration. Some atoms like silver will take electrons from the s orbital and promote it to the d orbital because they would rather have a half-filled 5d orbital than 4 for stability. Next we have isoelectronic atoms, which means it has similar electron configuration as an element after losing or gaining an electron. So let's for instance take this as an example. So a K plus 19, it loses an electron, it gets converted to 18 electrons. So it has 18 electrons, so that's an argon for instance, okay? And that's basically what an isoelectronic atom is. Next we have the excited state. When an electron jumps to a different state, you have for example oxygen. Oxygen configuration in ground state is 1s2, 2s2, 2p4. And then oxygen in excited state is 1s2, 2s2, 2p4, and 3s1. Okay, that's the excited stage, that it jumps into a different subshell instead of filling the p subshell first. And then we have atomic periodic trends. You have atomic radius. So the way atomic radius works is that it gets smaller as you go left and you go down. That's a atomic radius. And then you have ionization energy. So no, I'm sorry, I'm truly sorry. It actually gets bigger. It gets bigger as you go left and down. That's atomic radius, okay? And then you have electron affinity and ionization energy. Ionization energy is the energy required to remove an electron from the valence shell. So it goes up, it increases as you go up, and then go to the right. And then you got for instance oxygen as one of the most electronegative, and you got the noble gases as the most electronegative because it's so hard to remove a electron from a complete octet. Electron affinity is energy required to add electrons in a subshell. And then on the right side you have the non-metallic characters, left side is more of the metallic characters. And that's it. Thank you so much for watching, and please let me know if you have any questions or topics you want me to cover. And